Hi everyone, my name is Nicola Gnecco. I'm currently a PhD student at the University of Geneva. And first of all, I would like to thank the organizers for having me here today and for organizing such a nice online seminar. Today, I will talk about causal discovery in heavy-tailed models, which is joint work with Nikolai Mainshausen, Jonas Peters, and Sebastian Engelke. So the goal of the project is to retrieve causal information from observational data. And the idea is that we want to try to use the signal that lies in the tail of the distribution. And the reason behind that is that often causal relationships manifest themselves more clearly during extreme events. And examples of this range from Earth system science, climate science, or finance. To begin with, I'll just lay down the data generating process that we consider for this project. So here we have a linear structural causal model where each variable is depends linearly on its graphical parents plus some independent noise. And the assumption we make here is that the noise terms are heavy-tailed, in particular, regularly varying with a common tail index alpha. So regularly varying random variable are quite large class of distributions. For example, student T is one of them. And one can think of regular varying distribution as distribution where the tail is approximately power law. So before moving on, I just want to recall a few lines of work that also try to combine or bring closer the field of causality and extreme value theory. So the first one has been done by Nadine Giesibel and Claudio Kluppelberg, where they define and work within this special class of models called max linear models, which is quite different from the linear model that we consider. But they also have the noise terms that is heavy-tailed. And in a later work, what they showed is that under some condition, it is possible to recover a certain class of DAG from observational data. Quite different line of work, more in the Earth system science application, has been done by Philippe Navot et al., where they try to answer counterfactual questions such as what the Earth climate might look like without human intervention by relying and considering extreme climate events. Okay, at this point, I would like to introduce the probably main idea of the project, which is the causal tail coefficient. So here, consider two random variables, x1 and x2, with distribution function f1, f2, respectively. And for these two random variables, we define the causal tail coefficient as the expression below. So it's a conditional expectation, some limits are involved. So it's probably best to understand it by means of an example. So here we consider a very simple structural linear causal model, where x1 is some independent noise, heavy-tailed, and x2 is defined as x1 plus some other independent noise. And if we simulate from this data, this is one simulation on the right. So if we would like to compute the causal tail coefficient 1, 2, what we have to do is to condition on the first variable being large. And we can see that on this event, all the observation above the threshold correspond to quite large values with respect to the second variables. And this leads, in fact, in the limit, meaning if we push the the threshold to infinity, to the upper endpoint, or if it's rescaled to the uniform margin to 1, this leads to the causal tail coefficient to attain value exactly equal to 1. Vice versa, if we compute the causal tail coefficient in the other direction, well, what happens, we condition on the second variable being large, and we see that all the values above the threshold here correspond to both large and small values with respect to the first variable. And this leads the causal tail coefficient in the other direction to be strictly less than 1. So it's actually this asymmetry that we want to exploit later on to try to distinguish and infer some causal structure. So in fact, what we would like to do is to distinguish among these 6 causal structure if we're given 2 random variables. So when we have 2 random variables that are completely independent, like in the top left corner, where one random variable is causing the other. Also, we want to deal with somehow with the nasty case where the two random variables are confounded by a hidden variable x0, like in the bottom left. And of course, we can consider also combination of hidden confounders and causal effect. And in fact, what turns out to be true within the class of models that we just presented, so with heavy tail noise and same tail index, is that the knowledge of the causal tail coefficient really encodes the causal structure between the two variables. So what it means is that, for example, in the independence case, the causal tail coefficient is going to be equal to a half in both directions. On the other hand, for example, when one variable is causing the other, as we just saw in the example, the causal tail coefficient in one direction from the cause to the effect will attain value 1 in population case, and vice versa in the other direction will be strictly less than 1. And this even holds if on top of the causal effect there is a hidden confounder. And what's quite nice is that in the case of hidden confounder here, we see that when there is no causal effect between the two observed variables, the causal tail coefficient is strictly less than 1 in both directions. So far, I described what happens in the case of two variables, but of course, in general, one is interested to say something when the number of variables is larger than 2. So here we consider the goal of recovering a causal order pi of a heavy-tailed linear structural causal model. So we're still in the same setting, we just allow to have more than 2 variables. And briefly recalling what a causal order here is, so given a DAG, a causal order is an order over a DAG, or equivalently its corresponding structural causal model, such that all the parents in the graph appear before their children. So a valid order for this graph would be choosing the first variable, then variable number 4, 2, and 3. So of course, it's clear that for a given DAG, there might be more than one causal order, and vice versa. For a given causal order, there might be more than one DAG. However, knowing causal order is already quite useful, because if we assume that there are no hidden confounders, by performing regression according to the causal order would give us the causal effects. So the idea here is to estimate for each pair of the variables the causal tail coefficient and store it in a matrix P times P, and then use this gamma matrix as input for the algorithm that we name extremal ancestral search, or EASE by EASE. Now here, the algorithm is quite simple, but it takes a bit of time to explain it into detail. So I thought the best would to put a bit more details in the backup slides. So if you have questions, I'm happy later on to discuss. But what's quite interesting about this algorithm is that in the population case, it has the so-called oracle property, meaning that within the setting that we're considering, so linear models with heavy tail noise, if we denote by capital pi G the set of causal orders of the structural causal model, then if we give to the algorithm as input the causal tail coefficient matrix, then the algorithm will return a valid causal order. And this results even holds in the presence of hidden confounders, which is quite nice. Okay, so far I described causal tail coefficient in the algorithm in the idealized or population case. But of course, in practice, one has to estimate these quantities. So if we take a step back and we consider again 2 random variables x1 and x2 generated by a structural causal model possibly containing more than 2 variables, and we consider n independent copies of x1, x2, the most natural way to estimate the causal tail coefficient that we saw before is by means of a non-parametric estimator. So here what we do, we really replace the expectation by a sample average, the conditioning by the indicator function, where we denote by extreme being large a variable, we denote a variable being large if it's above some high order statistics. And conditional on this event, we take the sample average of this other random variable rescaled on uniform margins. So here what's important is the choice of the number of observations in the tail, okay, which is given by this parameter k. And in order to establish any consistency of this estimator, we need k to depend, of course, on the sample size. And in fact, it turns out that under some quite common condition in extreme value theory for Kn, the non-parametric estimator that I just presented is consistent. So it converges in probability to the population value. And what are the two conditions on Kn are the following. So we want intuitively that as the sample size increases, we also want the observation in the tail to tend to infinity, because we want to effectively be in the asymptotic regime. At the same time, we also really want to be in the tails. And to ensure that, we need that the number of observation in the tail grows at a slower speed compared to the sample size. So these are just these two conditions on Kn and are very common in extreme value theory. And of course, based on this result, on pairwise causal tail coefficient, we can also say something of what happens to our algorithm. So in practice, what one would do is to really start with a matrix X, which is n observation and p variables. One would choose the number of observations in the tails, this Kn, and would estimate all pairwise causal tail coefficient gamma hat. And then, of course, gamma hat would be the input to the algorithm is that would return an estimated causal order pi hat. And what's nice is that under the same condition as before for the Kn, the number of observation in the tail, the algorithm is consistent in the sense that the probability of returning a correct causal order tends to 1 as the sample size tends to infinity. Okay, so here I just want briefly to show a couple of simulations that would highlight hopefully the main traits of our method. So in the first setting, we consider a plain vanilla linear structural causal model where the noise is heavy tailed with common tail index alpha 1.5. And here we consider different methods. So our methods also lingam methods, pairwise lingam and ICA lingam. We consider also a variation on PC algorithm, rank PC, which deals with non-Gaussian data. And we also, as a baseline, use the random guessing, which basically is random guessing the causal order. As a metric, we use the structural intervention distance proposed by Jonas Peters and Peter Bullman, which we rescale between 0 and 1. So 0 would mean that the causal order retrieved is correct, and 1, it's completely wrong. And the experiment is performed such that we consider different dimensions for the graph in the x-axis and different sample sizes. And so the first thing we notice is that our method is consistent in the sense that as the sample size increases, it converges to the ground truth. And this even holds for the two lingam algorithm. It's quite interesting to notice, for example, here that the lingam algorithm have a quite faster speed of convergence, so to speak, meaning their performance is already better for lower sample size. And this is not surprising in the sense that lingam uses the whole data set, whereas we are only considering the observations in the tail. Now, in a second experiment, we simulated data again from a linear structural causal model where we added on top of that hidden confounders. And what we notice here is that while our method and also pairwise lingam still converge towards the ground truth, the ICA lingam, which was performing also very well before, starts to suffer a bit more, even when the sample size is quite large. And then as a final simulation, this is quite adversarial, but it's more as a sanity check that I will explain in a second. What we do, we simulate from, again, a linear structural causal model, and then we post-transform each variable by a monotone increasing transformation. In this case, in particular, by its distribution function. And the idea is that the causal tail coefficient only depends on the bivariate copula of the variables, and therefore it has to be invariant to monotone increasing transformation. And this experiment, in fact, confirms these observations. And of course, in simulation and even more in real data, what's very important is how to choose K, these, so to speak, hyperparameters, which is the number of observations we retain in the tail to compute the causal tail coefficient. And of course, what we want is that K must tend to infinity at a slower speed compared to the sample size, as we saw before. That's why here we consider fractional exponent of n. And what we ran several experiments. So for different tail indices, each point represents the performance of our method for different sample sizes and dimension of the DAG. And what we notice is that usually a good range of fractional exponent for K ranges between 0.3 and 0.5. And in particular, in the simulation I showed you before, and also in the application that will follow, we settled for a value around at 0.4, which seems to lie in the middle of this. And in fact, in the last section, I want to present briefly two applications. So the first one is a data set from a paper from Azadi, Davison, and Engelke from 2015. It's a data that consists of a river network where we have different stations, and at each station we measure the water level. And the goal is to recover only from the observations at these different stations the graph of the river network. So what we consider here is daily data over 50 years. And we only keep summer months, so June, July, and August, because during those months, it's more likely to observe heavy rainfalls. So this is the map of the river network. And what we observe are the red points, which denote the different stations. This is the upper Danube basin, where we know quite obviously what the ground truth is for the water flow, meaning that the water flows downhill. And then once it's in the Danube, it flows eastwards. And here, what we did, we applied our method to this data set. So this is the ground truth that we know if we drew a DAG. And if we estimated the causal tail coefficient based on this data set, and then we perform the EASE algorithm to obtain a causal order, we would retrieve a causal order that is correct. Of course, this is the causal order that the algorithm returned. It's not interesting per se, other than the fact that it's a valid one among the many that would be valid for this DAG. Now, in the second application, I would like to talk about financial data. And of course, in finance, it's extremely hard, if not impossible, to talk about causality. However, the time series that we consider, it's a bit special because here we have the euro-Swiss franc exchange rate at a daily frequency. And in red, I highlighted two turmoil period. And what's special about this time series is that in January 2015, the Swiss National Bank decided unexpectedly, so without any previous announcement, to unpeg the Swiss franc from the euro. So this can, in a sense, really be seen as an exogenous, or as an exogenous intervention in the system. And therefore, and during that day, of course, the impact of this decision of the euro-Swiss franc was very massive. And this propagated through the market quite clearly. And so for this reason, we would like to see whether if our method can detect, so to speak, this very large event, and somehow to detect also the direction from this euro-Swiss franc exchange rate to other variables in the market. In this case, for simplicity, we just consider the three largest Swiss stocks in terms of capitalization, so Nestlé, Novartis, and Roche. And what we do here, given this data, is the following. We start by estimating the causal tail coefficient for both tails. So far, I only described the case where there is a monotone increasing, so to speak, relationship between the variables. However, this was only to make the presentation a bit more intuitive. However, we defined also in our project this coefficient psi, which is a two-sided version, if you want, of the causal tail coefficient. Because in fact, in finance, a priori, we wouldn't know if one variable is positively or negatively related to another one. So we estimate all pairs for this coefficient psi, which has the same interpretation as the causal tail coefficient, and we store it into a matrix. And the way to read the matrix, so the exact value per se are not particularly interesting, other than the fact that the ways to read this matrix is something like on the rows of Euro-Swiss franc exchange rate, if the ground truth were this graph, of course, this is not the ground truth, we don't know, this is a hypothesis for the extreme day that we're considering, then the row corresponding to the Swiss Euro-Swiss franc exchange rate would have value 1 here if this was a cause for the Nestlé, Novartis, and Roche returns. On the other hand, each column can be read as how much the variable is caused by the others. So what we notice here, qualitatively speaking, is that the Euro-Swiss franc exchange rate is the least impacted or influenced by the other variables compared to the 3 stocks. And in fact, if we run the algorithm over this small matrix, we retrieve a causal order that is consistent, if we want, with the hypothesized ground truth that we postulated here. Also, we wanted to check how this coefficient is, so to speak, stable across time, so for different time windows. So here we consider a rolling window of 6 years. And what we consider is the pair of Euro-Swiss franc exchange rate and Novartis. What's quite interesting, again, it's probably more qualitative than anything else, is that the psi coefficient in the direction from Novartis to Euro-Swiss franc is quite constant across time, whereas it tends to be quite spiky in the other direction, corresponding to, well, the very turmoil, very extreme events that correspond. This was a turmoil period, and this was the very extreme decision from the Swiss National Bank. Okay, so to conclude here, today I presented a method that tries to estimate a causal order from heavy-tailed data by exploiting the signal that lies in the tail of the distribution. And we do so by proposing an algorithm which is computationally fast, and it's consistent as n tends to infinity. And the theoretical results even hold in the presence of hidden confounders. So if you are interested to read a bit more, we have our paper on the archive, and also recently has been published in the Annals of Statistics. So thank you very much for your attention, and I'm very happy if you had any questions.
Thank you. There are a couple of questions in the chat. Juan is also answering questions in the Q&A, so feel free to ask questions to either of the speakers. So one question that I actually find very interesting as well is the following. I was surprised to hear that we could recover the causal structure from data only, as my understanding so far has been that data cannot distinguish between correlations and causation without any input from substantive expert knowledge. Is this something special in the heavy-tailed case?
Yes, that's a very, thanks for the question. It's very relevant. And actually, yes, we exploit some, so to speak, stylized fact from heavy-tailed models. So I'm trying to keep backwards because I think that this example might give some intuition, hopefully, in the following sense. This data is generated from student T. So it's a linear model with student T noise. And what we observe here is that it's the idea behind this causal tail coefficient. Every time the cause is large, also the effect tends to be large. And this is due to by a result called max sum equivalence in heavy-tailed random variables. Whereas on the other hand, if we have the effect to be, if we observe an effect to be large, this can be because the cause is large, but also because the independent random noise is large. And this asymmetry is really key to exploit, it's really key to identify this causal direction. For example, if we tried with Gaussian noise, it wouldn't be possible because we would have a very symmetric case in both directions. And in fact, one can compute the gamma coefficient for the Gaussian noise, and there is no signal, meaning that it's exactly equal to 1 in both directions.
Following up on that, is linearity also important, or is it mostly the heavy-tailedness?
Yeah, we thought also a bit about that, but it seems like in the sense that actually the probably most stringent assumption is that the tail of the noise must be heavy tail with a common tail index. And what we saw in theory is that if we start to have different heaviness in the tails, then it's really hard to recover the causal effect, because there would be one variable that dominates all the other. Now, why am I saying this? Because if we start to introduce nonlinearities in the model, this would easily, if we start with all variables having the same tail index, then if I square one variable, of course, it has stronger tail, and so the method would not work anymore. So that's another, it's a good.
So we also have one more question for you before we. So about the finance example that you talked about, would anything change if the number of variables in the linear structure causal model would be large? And in the time series case, is the method applicable without correcting for time series properties such as autocorrelation or stationarity?
Right. Okay. Would anything? Well, regarding the first part, I'm not sure. I guess it's about the results. Well, this we didn't try with more variables, but in terms of computation, actually, it's quite easy because it's p squared with the number of variables, so it would be quite fast to compute. Regarding the second point, actually, we also ran some experiment after de-garching and using some arch model, and the results weren't particularly different. So we left. I mean, actually, it has to be like a very simple application. So we prefer to keep it like on the original scale. But that's a very good point. In fact, when one has time dependency, the best is to use an ARMA plus Garch model, for example, in this financial setting.